You are standing in a dark kitchen before sunrise, hearing the low buzz of a refrigerator and the faint hiss of a radio. Voyager 1 is a machine older than many grandparents, smaller than a room, and farther away than almost anything we can imagine. Right now, it is sending clues that connect Pluto, the edge of the sun's bubble, and the strange weather between the stars. Stay close to this channel for space stories built to make the deep dark finally feel understandable. The odd part is not that signals are arriving from far away. The odd part is what those signals keep saying when scientists line them up and listen carefully. A dead-looking dwarf planet turned out to be active. An old probe drifting in black silence turned out to be hearing a kind of hum. And the farther we look, the less empty the outer solar system seems. Pluto glows blue at sunset. Hydrogen light fills the sky more strongly than expected. Interstellar space itself seems to carry structure, pressure, motion, and memory. So this is not one mystery. It is a stack of them, spread from a frozen world past the Kuiper Belt and into the space beyond the heliosphere. Some are coming from instruments built before the internet existed. Some are coming from a mission that has already flown past Pluto and kept going. To see why this matters, we need to step back. Most people picture the outer solar system as the quiet part, where the action ended long ago and only leftovers remain. They picture Pluto as a frozen afterthought. They picture Voyager 1 as a heroic relic now mostly coasting through emptiness. That picture makes sense if you grew up with the old map. The inner planets felt busy. Jupiter and Saturn felt grand. Everything beyond that seemed like the backlot of the solar system, cold, dark, thin, and too far away to change much on human timescales. Pluto fit that story almost too well. It was founded in 1930 by Clyde Tombaugh, a young observer in Arizona, after a patient search through blinking star fields. For decades, it was a tiny, fuzzy dot. Then it lost planet status in 2006, and to many people it seemed to shrink twice, once in size and once in importance. Voyager 1 fit the same story in a different way. Launched on September 5, 1977, it had already done its great dramatic work at Jupiter and Saturn. It found new moons, new rings, and new textures in places humans had never seen up close. Then it flew on, farther and farther, almost like a postcard still moving after the trip was over. If you imagine both of them that way, Pluto as a fading footnote and Voyager as a fading signal, the outer solar system becomes easy to dismiss. It becomes a museum hall after closing time. A place where the lights are low and the labels matter more than the rooms. A place where the real discoveries are supposed to be over. That was never quite true to the scientists who kept watching. Alan Stern at the Southwest Research Institute spent years fighting to get a Pluto mission off the ground. He and many others thought Pluto was not a boring leftover at all. They thought it might be a key to the ancient solar system, preserved in deep cold. New Horizons was built from that belief. It launched on January 19, 2006, fast enough to leave Earth and race for the Kuiper Belt. It was not large, it did not carry huge power. It was a careful, efficient machine made to work where sunlight is weak and every watt matters. Even so, a lot of people still expected only a flyby of a cratered ice ball. They expected old scars and little motion. They expected thin air, simple chemistry, and not much surprise. That was the safe guess when the target is billions of miles away and barely wider than half the United States. The outer solar system even sounds quiet in the mind. No wind in trees, no surf, no birds. Only the crackle of radio traffic crossing hours of darkness before touching a dish on Earth. Even the images arrive with a kind of silence around them, as if the black background could swallow meaning. Voyager 1 made that feeling deeper. Its messages come so slowly that every command is an act of patience. In 2024, a one-way radio trip took about 22 and a half hours. By 2026, NASA was talking about a coming moment when the travel time would reach a full light day. That is the kind of distance that turns news into archaeology, and yet distance can fool us. Quiet is not the same as empty. Stillness is not the same as dead. A place can look frozen and still be changing underneath. A weak signal can still carry a new map of reality if the instrument is pointed at the right darkness. Scientists already had reasons to suspect that the far frontier was not simple. The sun blows out a constant stream of charged particles called the solar wind. That wind carves a giant protective bubble around us called the heliosphere. The edge of that bubble is not a neat, hard shell like the glass of an aquarium. It is more like a border made of pressure, particles, magnetic fields, and motion. Inside it, the sun still rules. Outside it, interstellar space presses back. For years, many models treated that border almost like a clean line in a textbook, a place you cross and then move into a calmer beyond. Pluto also sat inside a set of neat expectations. If it had an atmosphere, people thought it might leak to space in a fairly dramatic way. If it had weather, it would probably be weak. If it had surface change, it would be slow and ancient. A world that small and that cold was supposed to be running out of tricks. When New Horizons was closing in, scientists were ready for data. They were ready for geology, atmosphere readings, particle measurements, and long-delayed pictures. But even then, a deep assumption remained in place. The far edge of the solar system was expected to be important mostly because it preserved the past, not because it was busy in the present. Geoffrey Moore, the New Horizons geology team lead, later said Pluto was one of the most amazing and complex objects in the solar system. That line matters because it did not come before the flyby. It came after the evidence arrived. Before that, complexity was still something people had to earn the right to say. And while New Horizons was running outward, Voyager 1 kept doing something even stranger. It kept aging. Its parts kept surviving. Its instruments kept listening. Its power kept thinning year by year as its radioisotope generator lost about 4 watts annually, a slow fade measured in engineering choices. So the old picture held. Pluto was fascinating, maybe, but probably quiet now. Voyager was historic, surely, but probably reading a mostly empty sea. The outer solar system was the long, cold epilogue of the main story. That was the assumption waiting for a crack, but that picture is about to change. The signals coming from the edge do not behave like messages from a dead zone. They behave like pieces of a place that is active, layered, and still surprising us in real time. What we have taken for granted turns out to be only a small part of the story. Right the exact moment your old picture of the solar system started to bend. Those comments help shape which hidden pattern we turn into the next full episode. The crack really opened on July 14, 2015. New Horizons rushed past Pluto, and suddenly the little dot became a place with texture, light, weather, and attitude. Scientists expected an old, frozen face. They found mountains, plains, haze, and signs that Pluto had been far more alive than the safe version of the story allowed. One expectation was simple. A small, distant world should look ancient and heavily beaten up. What actually showed up was Sputnik Planitia, a bright nitrogen ice plain with surface patterns that looked young and renewed. It was like expecting an abandoned parking lot and finding fresh ice on a rink that someone had resurfaced overnight. Another expectation was that Pluto's atmosphere would be thin, simple, and maybe escaping fast. What New Horizons found, reported by Randy Gladstone and colleagues in Science in 2016, was a much colder upper atmosphere and an escape rate far lower than expected. The surprise was not a gentle trim to the old estimate. It was closer to learning that a roaring leak was really a quiet pinhole. Then came the view that still feels almost unreal. As New Horizons looked back after closest approach, Pluto glowed with layered blue haze. NASA described it as a photochemical smog, sunlight acting on methane and other molecules to build tiny particles that scatter blue light. A world most people imagined as gray and lifeless had sunset colors. The expectation there was colorlessness. The finding was stacked haze layers reaching more than 200 kilometers high, wrapping around a dwarf planet in the dark. The feeling is easy to miss if you only hear the numbers. It is like realizing the coldest room in the house has curtains moving in a breeze you never noticed. Pluto kept doing this. Scientists expected a simple ice shell and old scars. They found possible dunes made from methane grains, ridges, strange textures, and giant features like Reitmans that may be cryovolcanoes, meaning ice volcanoes. Instead of a locked freezer, Pluto looked more like a machine with hidden parts still shifting under the case. And Pluto's biggest moon, Charon, refused to stay simple too. New Horizons expected a more battered and plain companion. It found canyons, mountains, landslides, and sharp differences across the surface. The farther out the mission looked, the less the old idea of a sleepy frontier held together. This mattered for more than Pluto alone. It meant the edge of the planetary system was not just a storage shelf of leftovers. It was a place where chemistry, sunlight, nitrogen ice, and buried heat could still shape worlds. The small end of the solar system was not silent. It was just far. While Pluto was breaking one kind of assumption, Voyager 1 was breaking another. Voyager crossed the heliopause in August 2012 and became the first human-made object to operate in interstellar space. People often imagine that crossing is leaving a storm and entering a calmer ocean. The data said it was not that simple. At first, Voyager heard sudden whistles. These were plasma wave events, little sound-like signatures scientists convert from the behavior of charged particles. The expectation was that such events would stay rare and mostly depend on shock waves from solar eruptions. That would make the map of interstellar density patchy, like learning a city from a few lightning flashes. Then, Stella Koch-Acker at Cornell looked deeper. In a 2021 Nature Astronomy paper, with co-authors including Jim Cordes and University of Iowa researchers tied to the plasma wave instrument, she found something faint and persistent in Voyager 1 data. Not a burst, not a one-time event. A narrow, steady plasma hum. The expectation was silence between the whistles. The finding was a continuous tone that tracked changes in the density of interstellar plasma. Cornell described it as a gentle rain after the lightning. That comparison matters because it changes the scene from empty void to weather. Once that hum was noticed, the picture sharpened. Using it, researchers could track the density of interstellar material over a long stretch of space instead of waiting for rare solar outbursts. According to JPL's summary of the work, the electron density around Voyager rose roughly 40-fold from 2013 to about mid-2015. That is not what a flat blank beyond looks like. The expectation had been a fairly plain beyond, perhaps smoother once the solar border was crossed. What actually emerged was structure, motion, and changing density. It is like walking out of a bright room into fog and then discovering the fog has currents, layers, and pressure fronts of its own. The dark was not empty. It was active in ways we had never directly measured. That discovery did something subtle to the whole solar system story. It meant the edge of the sun's influence was not just a line we cross, it was part of a neighborhood. The interstellar medium, the thin matter between stars, was not background wallpaper. It was pushing back, shaping the heliosphere, and leaving fingerprints in the data. Then New Horizons re-entered the story in a new role. After Pluto in 2015 and Arakoth in 2019, it did not become a retired camera. It kept going deeper into the Kuiper Belt. By October 1, 2024, NASA said it had reached 60 astronomical units from the Sun, twice as far out as Pluto was during the flyby. That distance changed what New Horizons could see. Closer to the Sun, ultraviolet measurements are flooded by sunlight scattered through the solar system. Farther away, the glare drops. So the spacecraft's ALICE instrument, an ultraviolet spectrograph, could start reading the wider background more clearly. That turned the ship from a Pluto visitor into a sky watcher. Scientists had long talked about a possible hydrogen wall near the heliosphere. The basic idea was that interstellar hydrogen should pile up at the boundary, making a detectable glow in Lyman alpha light, a specific ultraviolet wavelength linked to hydrogen. The expectation was neat. Find the wall, and you find a major piece of the edge. But when Randy Gladstone and the SWRI-led New Horizons team analyzed broad sky scans, including an extensive set from 2023, the picture shifted again. In April 2025, they reported in the Astronomical Journal that the Lyman alpha background looked roughly uniform and about 10 times brighter than earlier estimates suggested. And they did not see evidence that a hydrogen wall was a major source. The expectation was a bright signature from a piled-up wall. The finding was a much broader glow, possibly tied to hydrogen in the shell of a hot local bubble around our solar system, shaped by old nearby supernovae. That is like going outside to find one campfire and realizing the whole horizon is faintly lit. The map got larger and the border got less tidy. Alan Stern called those observations landmark work. He said they revealed new characteristics of the sky around the solar system and refuted older ideas the New Horizons data did not support. That is careful scientist language, but the meaning is strong. A mission built to visit Pluto was now helping redraw the ultraviolet surroundings of our stellar neighborhood. And here's where the story earns some humility. Even the teams doing this work do not think every piece is settled. Acker and her colleagues were still working to pin down the physical model behind Voyager's steady plasma emission. Gladstone's result points strongly away from one old picture, but not every detail of the brighter glow is closed. That hesitation matters. It keeps the story honest. The outer solar system is not sending us clean schoolbook answers. It is sending hints, tones, sky maps, and pressure clues that scientists still have to argue through. The frontier is not only far away, it is still partly untranslated. Then the weirdness got even more literal. In November 2023, Voyager 1 began sending unreadable science and engineering data. To anybody outside mission control, that looked like a bad ending. An old spacecraft, more than 15 billion miles away, seemed to be speaking nonsense from interstellar space. The expectation was grim and simple. A machine built in the 1970s had probably reached the point where a deep failure could not be fixed. What engineers found in early 2024 was stranger and more hopeful. About 3% of memory in Voyager's flight data subsystem had been corrupted, likely because a chip wore out or got hit by an energetic particle. That sounds tiny, but on a spacecraft this old and this distant, tiny failures can become giant problems. The flight data subsystem packages science and engineering information before it goes out through the radio system. If part of that memory breaks, it is like a librarian losing the labels on a whole shelf. The books still exist, but the order is wrecked. So the team at NASA's Jet Propulsion Laboratory got creative. They could not repair the bad chip directly. Instead, they divided the damaged code into sections and moved those sections to different places in memory. Then they had to update all the references so the code still behaved like one whole program. The expectation was that deep space would turn delay into defeat. But in April 2024, after a 45-hour round trip for the radio conversation, engineering data began to come back in readable form. Later, the rest of the science stream was restored as well. It was like rebuilding part of a typewriter by mailing it instructions one letter at a time. This was not just a nice save. It showed that even at that distance, Voyager 1 is still part of an active conversation. The spacecraft is not a drifting fossil. It is a working instrument platform, fragile but still responsive. And the things it measures still matter because no other craft is out there doing the same job. By 2025 and 2026, power had become the next pressure point. Voyager's generator keeps fading. NASA shut off the cosmic ray subsystem on Voyager 1 on February 25, 2025, to save power. Then on April 17, 2026, the low-energy charged particles experiment was also turned off. The expectation might be that shutting down instruments means the science is basically over. What actually remains are the two tools now most central to this story. Voyager 1 still has its magnetometer and its plasma wave subsystem running. The craft can still measure magnetic fields and still listen to plasma waves in a region no other human-made machine has reached. Kareem Badarudin, Voyager mission manager at JPL, said those two remaining instruments are still working great. NASA also said the shutdown bought roughly a year of breathing room while engineers prepare a bigger power-saving change they call the Big Bang. Even the nickname tells you the mission is not sleepwalking. It is improvising to stay alive. So when people ask what is happening right now, the answer is not one event. It is a live chain. Pluto changed what a distant world could be. New Horizons changed from a flyby mission into a heliophysics outpost. Voyager turned interstellar space from abstraction into measured weather. And here is where this stops being about one spacecraft and begins being about us. If these reveals hold, then the way we think about distance quietly changes. The far edge of the solar system is not where the story fades out. It is where a new kind of story begins, one built from weak signals, patience, and revision. Share this with the one friend who still thinks deep space is just empty black nothing. That handoff matters because this story lands best when one old idea gets replaced in real time. What changes now is not only the science, it is the mission of attention. Scientists are no longer just cataloging old, cold objects in the outskirts. They are treating the outer solar system and the local interstellar medium like an active environment, with weather, structure, chemistry, and moving boundaries. That shift affects what gets built next. New Horizons is still healthy and still moving outward at about 300 million miles per year, according to NASA. Johns Hopkins APL describes it as hurtling toward the doorstep of interstellar space while measuring dust and the heliospheric plasma environment. It is not done being useful just because Pluto is behind it. Voyager 1 is also not done, even in its stripped-down state. NASA's 2026 updates say the remaining plan is to stretch operations through further power-saving work. Tests of the Big Bang approach were scheduled for Voyager 2 in May and June 2026. If those tests worked, Voyager 1 could get the same fix no sooner than July 2026. That is the strange beauty of this moment. A spacecraft launched when disco was on the radio may still be teaching us how the sun's bubble meets the galaxy. A Pluto mission may still be telling us how hydrogen light fills the sky far from solar glare. The machines are old, the discoveries are current. There is also a human lesson in the timing. At home, we are used to fast answers. A text arrives in seconds, a map updates live. But a command to Voyager 1 takes roughly 23 hours to get there now, and another 23 to hear back. Patience is not a virtue out there. It is the whole operating system. That patience is about to gain a number people can feel. NASA says Voyager 1 is approaching a milestone on November 18, 2026, when it will be one light day from Earth. That means a signal moving at the speed of light will need 24 hours to reach it. The distance is about 25.9 billion kilometers, or 16.09 billion miles. A number like that can sound dead if you let it, so shrink it. Imagine setting a note on your kitchen table today and only hearing the table answer tomorrow. That is the conversation line with Voyager now. It turns radio into time you can almost touch. The scientific questions are getting sharper too. How exactly is the heliosphere shaped by the local interstellar medium? Why is the Lyman alpha background so much brighter than older estimates suggested? How much of the signal comes from the shell of the hot local bubble around us? Where does the sun's influence really stop mattering in the data? There are planetary questions still hanging in the air as well. How active is Pluto beneath its crust? How long can a world that small keep internal heat and perhaps a buried ocean? How does its atmosphere change over long seasons as it moves on its stretched path around the sun? A flyby solved many mysteries and multiplied others. That is normal in real exploration. A good mission does not close the book. It teaches you the book is part of a shelf you had not noticed. Pluto was never only about Pluto. Voyager was never only about endurance. Both are telling us how edge regions shape the whole system. Researchers are already thinking past them. Pontus Brandt and others at Johns Hopkins APL have written about New Horizons as a unique platform for future study of the outer heliosphere and the local interstellar environment. There are also long-running ideas for a dedicated interstellar probe. The dream is simple to say and hard to build. Go farther with instruments designed from the start for the crossing. That future matters at home more than it first appears. The heliosphere helps shield the solar system from some galactic cosmic radiation. Its shape, motion, and pressure are not trivia. They are part of the broad environment that surrounds every planet, every mission, and every human body beyond Earth's own magnetic cocoon. The edge is remote, but it is not irrelevant. Even the language of these missions changes how we live with uncertainty. A strange hum in the data is not dismissed. It becomes a clue. A brighter than expected ultraviolet sky is not an embarrassment. It becomes an invitation. A garbled spacecraft message is not necessarily an ending. Sometimes it is a puzzle that forces better engineering. The dates make that feel real. April 17, 2026, one more Voyager 1 instrument went dark to keep the mission alive. May and June 2026 were set aside for Big Bang testing on Voyager 2. No sooner than July 2026, the same approach could be tried on Voyager 1. November 18, 2026, the one light day milestone arrives. Those dates are not just items on a schedule, they are the clock ticks of a fragile conversation at the edge. Every one of them asks the same thing. How long can we keep listening? And what will the next faint change in the background force us to redraw? New Horizons brings its own precision. It passed 60 astronomical units from the Sun on October 1, 2024. Its 2023 Lyman alpha scans covered roughly 83% of the sky. The 2025 team result pointed to a background about 10 times brighter than expected. Those are not vague wonders. They are measured corrections to the map. Voyager does the same with a different mood. One aging craft, two surviving science instruments, a one-way radio delay nearing 24 hours, a future stretched by watts, code shuffling, and careful risk. That is exploration stripped to its bones, and it is still enough to move the story forward. And the story will move forward. Somewhere ahead, another pressure front will pass Voyager. Another quiet shift in frequency may show that interstellar density has changed again. Another New Horizons analysis may sharpen the shape of the ultraviolet sky around our solar neighborhood. Tomorrow's surprise will probably arrive as something small. Not a giant explosion, not a Hollywood alarm. A line in a plot. a tone rising a little, a brightness that does not fit the old model. That is how the frontier speaks when the frontier is measured in thin gas, dim light, and machines almost 50 years old. So narrow the whole thing down to one image. An old spacecraft is out beyond the heliosphere, running on leftover warmth from decaying plutonium, listening with one plasma wave instrument and measuring with one magnetometer. Its radio takes nearly a day to cross the dark, yet it still turns that dark into evidence. Set a reminder for November 18th, 2026. That date will give you a personal handle on the scale of this story, and you will never hear the phrase deep space the same way again. And keep one more picture beside it. Pluto, lit from behind, wearing blue haze and thin, stacked bands. The world we once treated like a cold dot turned out to glow. The space we once treated like empty black turned out to hum. That is the pattern worth carrying forward. What the future likely holds is not silence. It holds better listening. It holds more careful maps of the border between the sun and the galaxy. It holds new machines built because these old ones prove the border is alive with signals. And it holds the quiet confidence that the next impossible message is already on its way.